Okay, so this lecture combines two sections, 3.4, 3.5, and focuses on algorithms for whole number multiplication and division. And I'm going to start off with reminding you the definition of an exponential expression, what a to the power n stands for, and then we're going to review the rules for exponents. So a to the power n is a times a times a basically multiplied by itself n times. So we have n factors of a. A is here called the base and n is the exponent. And a to the power 1 is just a. Okay, so we have this. Now let's look at the rules. Maybe before we move on, so examples. So 5 to the power 3 would be 5 times 5 times 5, right? 3 factors of 5, where 5 is the base and 3 is the exponent. Now, what are the rules? Some rules are pretty intuitive, so I'm going to try to always back it up by the example. And the first rule would be the product rule, which states that a to the power m times a to the power n is the same as a to the power m plus n. So basically you can combine base-like expressions when you multiply, and that becomes 1 base a, and you just count how many factors of a you have all together, and that would be m plus n. You're gonna see it on an example. Let's look at 7 to the power 2 times 7 to the power 3. How many factors of 7 I have all together? 7 squared is 7 times 7. This is a product, so I continue, and 7 cubed is 7 times 7 times 7. So when I look at this product all together, now I ended with 5 factors of 7. So 2, right, and plus 3. So combined, I have 5 factors of 7. So that becomes 7 to the power 5. And that's what the product rule is about. Now, if you have the similar, when you divide, it will be kind of similar story, but we're going to be subtracting the powers, because however many factors of a you have in the denominators, they will cancel that many factors in the numerator. So that will be decreased by n. Let me give you an example. So here it says, if you divide a to the power m by a to the power n, that becomes a to the power m minus n. Okay, so let's look at this example. Let's do 7 to the power, let's say 5, divided by 7 to the power 3. So what I'm saying here is that, notice, the top has 5 factors of 7. The bottom has 3 factors of 7. So those 3 factors of 7 from the bottom can cancel, right? 3 factors of 7 on top. So now I have, instead of 5, I have 3 less than 5. I have 2. 7 squared. Okay? Because again, I need to take away those 3 factors of 7, because that would be cancelled, right? So I end up with 7 to the power 2. So that's a difference of the powers. And now, so we were talking base-like expressions. So what if the base is the same? So if the base is the same, but we multiply or divide the base-like expressions, then we can combine them into one exponential expression, right? In case of the product, it would be the same base to the sum of the powers. Instead of the quotient, would be the base stays and to the difference of the powers. Now, what if you have one base, but one power after another? So this is this. So we have a is raised to the power m, but then is raised to the power n. That becomes a to the power m times n. Example, to illustrate that. Let's say we have 7 to the power 2 and then to the power 3. Okay, so according to that rule, it should be 7 to the power 6. 2 times 3. I'm multiplying the powers, not adding. But I want you to see it why. So when you think of it, let's work from the inside, right? 7 squared is 7 times 7. But now this has to be raised to the power 3. So which means 7 times 7, now my base, has to be multiplied 3 times by itself, right? So now we have 3 times 2 factors of 7. So if you count how many factors of 7 you have altogether and you can erase parentheses, you would end up with 6 factors of 7, right? Because we had 3 times 2 factors of 7. So 3 times 2 gives me 6 factors of 7. And finally, if you have, what happens if you have 2 different bases, and that's, by the way, the same. I'm going to add one more thing because it's the same for the division. If you have 2 different bases but the same power, so now what connects them is the power. You have the same power. You can basically, or then you can, thinking from the right to the left, it might be easier. You can distribute the power among the products. So that's a to the power n times b to the power n is the same as if we first multiply a with b and then raise to the power n. Same story is for the I'm not going to give you example here because I want to move on to examples, but same story is with the division. If you had the division, so 2 different numbers raised to the power n, you can really raise to the power n each of them separately. So again, the power can be distributed among products and quotients, but not among sums or differences. This is very important, guys. Not true. This one is not true. If you had a plus b to the power n, then it's definitely not a to the power n plus b to the power n. I'll give you an example to show it's not true. If you had 2 plus 3 to the power, or not to have the same, let me do 1 plus 3 to the power 2, it's not the same as 1 squared plus 3 squared, right? Why? Because left hand side is 4 to the power 2, which is 16, and the right hand side, 1 squared plus 3 squared, is 1 plus 9, which is 10. Definitely not the same. Left and right hand side are not the same. So I kind of want to alert you to that. Many students make this mistake. The powers, exponents, cannot be distributed among sums or differences, only among products and quotients. Okay. And before we move to the last example, examples, I want to just point out this, that if those rules were to be true, then notice that a to the power 0 times n would be a to the power 0 plus n, right? If you have base-like expressions, so the same base but different powers, you keep the base and you add the powers. But then that would mean that, which is just a to the power n, but then that would mean that a to the power 0 must be 1. Because a to the power 0 times a to the power n is supposed to not change a to the power n. It's the same as a to the power n, which means a to the power 0 has to be 1. So that's why we add in this definition, we can state it or we can conclude it either way, that with those properties and with the original definition, it must be that a to the power 0 is 1. Some treat it as a definition, not a consequence, but for things to work out, a to the power 0 has to be 1. So let's look at the examples I have here. Simplify each of the following using properties of exponents. So notice you have base-like expressions, the same base, just different powers. So you keep the same base, 5, and you add the powers, right? When you multiply, you have to add the powers. That's it. I'm not expecting you to calculate it. Calculators, you can type it in, but it's going to be a huge number. Okay, now we have base-like expressions. Again, what's in common with all those 3 factors is the base. So if you have the same base 6 and you multiply the expressions, then you can keep the same base and you have to add. And we showed it that it works for pair, but really it works for 3, 4, as many factors as you want. but if you wanted, you could group and do first 2. That would be 6 to the power 12, and then 12 plus 3 would give you 6 to the power 15. But basically, you can just add the powers, okay? So let me make a note. If you wanted to use exactly the properties above, you could say, okay, I'm going to first multiply those two, but that's 6 to the power 12, and then you would end up again multiplying those two, and that would be 15 if it went by pairs. But ultimately, this product rule expands to as many factors, base-like factors as you want to have. Okay, so that's 10 to the power, and you just have to add the powers. So that's going to be 10 to the power 313, right? Again, I'm not expecting you to calculate how much it is, okay? And final one, D. Well, let's be careful here. We do not have base-like expressions. However, we have the same exponent. So what I'm seeing here, what kind of connects those two factors is the power 7. So let's set them aside. Again, it's not quite the similar example to the previous one. Let me set aside those, because 10 to the power 5 seems like it doesn't have much in common yet with what I have, but those two, even though they're not base-like expressions, but they have the same exponent. And when I have the same exponent, I can multiply first and then raise to the power 7. Or, right, instead of this power 7 being already distributed. So that will give me 10 to the power 7. Now I do have base-like expressions. Now the base is the same. And when base is the same, that common base stays, because I'm counting how many factors of 10 I have all together. Well, 7 plus 5, I have to add the exponents. So that's going to be 10 to the power 12. Okay? Okay, let's look at the next one. Which is greater, 2 to the power 80 plus 2 to the power 80, or 2 to the power 100? Okay. Let's see how I can compare. If I had them both in the base 2, right, then if I could write this as 2 to some power, then I will know how to compare it with 2 to the power 100. The smaller the power, the smaller the number is, right? Okay, so that's going to be my goal. So what I see, 2 to the power 80 times 2 to the power 80 is twice 2 to the power 80, right? Because if you don't see it, we can, those are like, we can factor 2 to the power 80 out. But before we do that, let's be clear to point out what factor then stands in front of it. If you don't have anything, think of it as 1 times. So now if you were to factor 2 to the power 20 outside, whether you put it in front or behind doesn't matter, and multiplication order is commutative, that becomes 2 times 2 to the power 80. And now remember, 2 is the same as 2 to the power 1, so I can write this power 1. And now we do have base-like expressions that we're multiplying. So now I can write that combined I have 81 factors of 2, right? Because I'm adding the powers. So that means 2 to the power 100 is bigger than 2 to the power 80 plus 2 to the power 80, which ended up being 2 to the power 81, right? Because again, 2 to the power 81 is a smaller power than 80. A smaller power than 100, which means, 2 to the power 81 is smaller than 2 to the power 100. Okay, let's look at one more of this type. Which is the biggest? Let's compare it. So this will be a little bit different because here is 2 to the power 100, and the middle one is 3 times 2 to the power 100. Okay, so let's kind of express every term here as some number of 2 to the power hundreds. Okay, let's see if we can do it. So let's set aside one factor of 2. If I take one factor of 2 aside, then what's left is 100 factors of 2, right? Because I set one factor of 2 aside, so instead of 101 factors of 2, I have 100. So now I see that this is it. Now the middle number is 3 times 2 to the power 100. So now I know it's bigger than 2 times 2 to the power 100. But let's write also, so this middle one is nice the way I want. But let's also write 2 times to the power 102. I want to get 100 power, which means I have to set aside 2 factors of 2. So that now combined is again 102 factors, right? If you were to add again back those powers, that's 102. But 2 squared is 4 times 2 to the power 100. All right, so which one is biggest? Well, that's the smallest. That's middle. And that's the biggest. Right? Because we have 2 to the power 100 twice, 3 times, and 4 times. So 4 times must be the biggest. Which was the question. Okay, let's look at multiplication algorithms. We're again gonna I want you to be familiar with the concrete model, something you're gonna have to show in school, then expanded algorithm, and then standard algorithm. Okay, so concrete one, let's multiply 12 times 4. So in the concrete algorithm, what you would do, 12 stands for 1 long and 2 units. And I want you to place them horizontally when we multiply. So this, just to be familiar. And times 4 means making 4 copies of those. So I would combine, I want to have 4 copies of 1 long and 2 units, which is exactly here. And then when I calculate, I'm going to calculate that I'm going to end up with 4 longs and 8 units. So with the number 48, that's what concrete models show me. But ultimately what happened is like I copied the longs. So I copied 10 and I also copied the units. So how we can look at 12. 12 is the same as 10 plus 2. So when you're multiplying by 4 means multiplying 2 by 4 and 10 by 4. That's why I could just focus on multiplying by 4 each kind of power of 10 units, then longs. If I had flats, I would be focused on multiplying them by 4 because ultimately that's, if I split the number into number of longs plus number of units, so in this case 10 plus 2, I can multiply each separately. So that gives me a combined 48. So this is like this expanded algorithm where you focus on multiplying 2, and then you focus on multiplying 10, and then you combine them, right? In the standard algorithm, you just do 4 times 2 is 8. And you multiply 4 times 1, although you know that it means 4 times 10, but you already are combining those into 1. Now, multiplying by 10 usually means whenever if you were to make copies of 10 longs, it would create a flat, right? So if you multiply by 10, a long will, since it's 10 longs gives you a flat, right? So longs will multiplied by 10 become flats. So units multiplied by 10 become longs. And flats multiplied by 10 become blocks. And of course, above that dimension, we don't have this concrete model visualization. We can only visualize till 10 to the power 3, till all the way up to blocks. Okay, so let's look at this kind of writing here, because I want to explain why you can actually, when you're multiplying, you can focus on multiplying sorts of longs, flats, units, whatever, and blocks kind of separately. Well, it comes from this, because that's what expanded algorithm does, and let me show the example here. So if you want to write 367, as remember in base 10 it means 3 times 10 squared, 6 times 10, and 7. What basically means we have 3 flats, 10 by 10, 6 longs, 10 units long each, right? And then 7 units. Okay, and you want to multiply that number by 4. Multiplication can be distributed, so let's distribute the multiplication by 4 among each term. So this needs to be multiplied by 4, this needs to be multiplied by 4, and this needs to be multiplied by 4, which is exactly what's written here. Of course, then you also have an associated law of multiplication. So the grouping can be that parentheses can be grouped this way, that first 4 and 3 needs to be multiplied. Here, first 4 and 6. So what it means is basically having 3 flats, now I have to make 4 copies of them, 4 times 3. And that will give me 12 flats, or 1200, right? Here's 4 times 6, that's 24 times 10, so 240. And here's 4 times 7, 28, and you add them together and you have it. So this, if you write it as in your expanded algorithm, this would be as follows. 4 times 7, that's 28. 4 times 60, that's 240. And 4 times 300, that's 1200. Okay. And if we align, first we always multiply units because we can align them nicely. Then we multiply tens. So that's 4 times 6 is 24, but 24 tens, so 1 0. And then 4 times 3 is 12, but that's hundreds, so we need to add 2 zeros. And when we align this way, we can then add together and we have it, right? I remind you that in the that's expanded algorithm, but I'll remind you that in the standard, right, algorithm here, so this is, by the way, this is where it went, this went here, and this one here. In the standard algorithm, not expanded, you would do 4 times 7, 28, 8, and you would carry 2. It's like saying I have 28, 8 units and 2 longs. Now 4 times 6, right, which is really 4 times 60, so that's already longs, right? I'm counting how many longs I have. That's going to give me 24 longs, right? But with this 2 already there, combined is going to give me 26 longs. Okay. So I have 26 longs, but I only keep 6 longs because those 20 will become really 2 flats, right? Because 10 longs become a flat, so 20 longs become 2 flats. And then 4 times 3 is 12, right? Which now I'm really counting how many flats I have. So 4 times 3 is 12. Add 2 flats that I set aside from the previous operation. So combined I have 14 flats. But 14 flat is really 4 flats and 1 block, right? So that's why it went to the next place. And that's, of course, is the same 1468 as with the standard algorithm, with the expanded algorithm. But okay, use now, so question 3, use expanded notation and an approach similar to the preceding to calculate this. So expanded notation, first I want to sort of do it this way, and then we're going to do expanded algorithm. So in expanded notation, what I want is to write this number. That's number of units, right? That's number of tens. That's number of 10 squared. That's 10 cubed. We're going to just keep in mind that at the end of this section, we're going to work with different bases, right? So if you, when base changes, it's going to be similar, but instead of powers of 10, you're going to have power of whatever your base is. So that's, I have 4 times 10 cubes. This is 5 times 10 squared plus 8 times 10 plus 9. And then we're going to distribute the multiplication by 7 among all the terms. So 7 times 4 times 10 cubed plus 7 times 5 times 10 squared plus 7 times 8 times 10 plus 7 times 9. And remember, associative law of multiplication allows me to move the parentheses when I multiply. So basically group, multiply any pair I want in my product. And what now I can start multiplying. That's giving me 28. Remember, that's blocks. This gives me 35 10 squared. That's going to give me 56 tenths and 63. So this is 28 and 3 zeros because that's 10 to the power 3. This is 35 and 2 zeros because that's 10 to the power 2. That's 56 and 0, and this is 63. And then you sum it up. You can use a calculator and you will get this, right? Now, when you use expanded algorithm, you're going to get similar stuff, but now remember we want to take this number as before and multiply it by 7. So what happens is number of units, right? Let's go first. 7 times 3. Then number of 7 times 8 is 56, right? And 0 because that's number of tens. 7 times 5, that was 35 and 2 zeros. And 7 times 4, that's 28, right? And 3 zeros. So you will put it all together. And in this now it's easy to add them. Maybe easier than before. 6 plus 6 is 2. That's 11. So 1 and 1. That's 12. So 2 number of units is 2 and 1 carries over and 3. Okay, so the same as before. So now this expanded algorithm kind of matches this this writing right above. That's where it came from. Okay, so let's focus now on a concrete model. What happens when you multiply with 2-digit factors? So instead of multiplying by 3 or 7, now we're going to be multiplying by 14. So how that plays a role? Well, first, remember multiplying by 10 is just kind of changes the units to longs, longs to flats, flats to blocks, right? So adds a 0 at the end. And if you look at, so say we want to multiply 23 times 14. So first I line up 23 horizontally, 2 longs and 3 units. Okay, so that's the beginning. Once I'm done with that, I'm going to focus on multiplying 4 times 3 and 4 times 20. And then I'm going to multiply 10 times 3 because 14 consists of 10 and 4, right? So, and then 10 times 3 and 10 times 20. Because ultimately what that, if you write it down, how you can represent when you want to do 14 times 23. As before, you would write that would be 10 plus 4, and you multiply 20 plus 3, 2 times 10 plus 3. Okay. So therefore, when you start distributing, right, you would have, it's kind of like foiling, you would have 4 times 3, you would have 4 times 20, but you also would have 10 times 3 and 10 times 20. Okay, So that would be 4 times 3 plus 4 times 20, and also 10 with 3 and 10 with 20. And all those products you can line up here. But how that plays out in the concrete model? So first multiply the units by 4 times 3, which means that 3 units are having now 4 copies of 3 units. Then 4 times 20, so 20 means 2 longs, so make 4 copies of it. Okay, so 2 longs now copied 4 times. Okay, now then we're going to do 10 times 3, so now that means 3 units we had originally. When you multiply by 10, they will become long, so this is this 10 times 3. And then we're going to do 10 times 20. That means that 20 stood for 2 longs, but when you multiply it by 10, each long will become a flat. So this is it. This is 200, right? Because each flat is 10 by 10. Each flat has 100 units in it. And that's the expanded algorithm, and then you add it all together and you have what you need, which you also can write. So this expanded algorithm here, right, you can also write in standard algorithm. And how do we work on it? Well, we do 4 times 3, that's 12. You write 2 and you say, okay, and then 1 long. And then 4 times 20, now we multiply longs. That's gonna give me 8 longs, and then plus 1 long I had, so that's gonna give me 92. So basically 23 was multiplied by 4 and combined it gave me 92. Okay, so 4 times 3 was 20, which means 2 units 1 long. 4 times 2 is 8 longs, plus and 1 I carried over, that's 9 longs, so 92. Then next I'm gonna do 10 by 23. So that really becomes 230. So I do 1 times 3 and 1 times 2, but sometimes we don't write it 0, we just move it like here. We just leave a room to indicate that that's really now the number of tens, right? So I'm moving one place to the left, so when I add, it's going to be aligned correctly. But remember, that's the same as 230. That's 10 times 23. And then you're going to add those two and you have your answer, okay? Okay, so let's look at the next question to understand the kind of model. So the following model illustrates 22 times 13. Okay, and explain how the partial products are shown. So basically I'm going to mark on the picture, and then we're going to draw a similar model for 15 times 21. Okay. And guys, it really doesn't, since the order in the product doesn't matter. It doesn't matter if I do 13 times 22 or 22 times 13. It doesn't really make a difference. So what they do here, they place 22 because they put 2 longs and 2 units on the bottom. But they already, here what you see are 3 copies of it. So basically this 10, so this is 2 units multiplied by 3, right? So this is 3 times 2. Okay, this corner here, or let me write the same way as they wrote above, this is 3 times 2. Okay, 3 times 2. The next one is 3 times, so we had 22 had 2 longs and we made 3 copies of it. So this is 3 times 20. 3 times 2 longs, right? So this one here is 3 times 20. Okay. Now this corner here is now those 2 units, it became longs, because when you multiply by 10 it just created longs, right? So this is 10 times 2, this corner, and the left corner, this one is we had 2 longs, right? So that was 20, and you multiply by 10, so each long became a flat. So again, originally, I'm gonna write down what you had originally. Originally you had 22, 2 longs and 2 units, right? And when I multiplied by 10, each long became a flat and each unit became a long, and this is what's illustrated on top, right? Here, this top part. And the bottom part is just, again, we started with 2 longs, 2 units, and if you multiply them by 3, well, then you're gonna have 3 copies of those, right? And that's represented in the bottom part. Okay. So that, I hope you saw it. Let's draw a similar model for 15 times 21, and then it's up to us. Do we put 15 and multiply it by 21, or 21 and multiply it by 15? It really shouldn't make a difference. So I'm gonna put the bigger number. I think it's always easier, and then I'm gonna be copying it. But you could have put 15. I'm gonna put 2 longs, 21, which is 2 longs and 1 unit. That's 21. So first I want to multiply it by 5, 21, and I'm gonna write it here. So that's, and maybe you guys, let me go back. I should have written it here. 22 times 13. So remember what we did. 3 times 2 was 6. 3 times 20 was 60. Then 1 times, or that's really 10. 10 times 2, right? That gave me 20. That was this corner. And 10 times 20 gave me 200, right? Three times 2. And then you can count this all together. That's 286. That was the previous one. I forgot to write this. So let's do the same for 21, and I'm doing 21 times 15 instead of 15 times 21. It's the same, but we can do the other way around as well to practice it. So in that context, I first focus on multiplying by 5. So I'm going to multiply those units by 5. So so that's now will become 2, 3, 4, 5. So this corner here is 5 times 1. And I'm gonna also make 5 copies of longs. So now this corner, that's 5 times 20, 2 longs. 20 is 2 longs multiplied 5 times. Okay, so that's 5 times 20, which is 100. And this is 5 times 1, okay. Then now I have to multiply by 10, because 15 is 10 plus 5, right? So that 10 here. So then 1 long now, 1 unit now will become a long. So this is 10 times 1. And then each long multiplied by 10 will give me a flat. So this corner here, right, is 10 times 20. So I have 10, this gives me 10 times 1, and then 10 times 20. right? So when you count it all together, you have 315, and you can count how many you have. This gives you 2 flats, but here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 longs. That's another flat. So you have, so this would become a flat, right? So you have 3 flats, 1 long and 5 singles, 315. That was 21 times 15, and let's do the other way around. Let's do 15 times 21, meaning let's put here 15, 1 long and 5 units. So the other way around. And let's multiply by 21 just to practice. So notice I will have 1 times 5 and 1 times 10, and then 20 times 5 and 20 times 10. So first I will multiply by 1, so basically that's it. I don't have to make any copies. It is what I drew, both 5 and long, right? So I have this corner is 1 times 5, and this is 1 times 10. Then I have to multiply by 20. So so basically multiply, not only make 2 copies, but also long will become a flat. So this and the unit will become a long. So now what's gonna happen, that each I will have each, that's multiplying by 10, each unit becomes a long, but then 20 means 2 copies of those. And here each long will become a flat, but again 20 means 2 copies of those. So this is 20 times 5, this corner, and this corner is 20 times 10. Okay, so when you count what you have again, those will give you a flat, because this is 10 longs, so this will become a flat. Oh, well, let me maybe fill in here. That's 120 times 5, and this is 220 times 10. So of course final answer is the same, and also from the concrete model you will see the same final answer. 3 flats, 1 long, and 5 singles, which could be seen on the expanded algorithm as well. Okay, and then we have this nice remember for addition we had this like scratch algorithm. For multiplication you have the and we also had lattice algorithm for addition. I haven't used it that much, but we had it. For multiplication, you also have the lattice algorithm, and that one sometimes comes in handy. So what happens here, say you want to multiply 14 times and with 23. So you put one on top in a row, the other in a column. You create a grid, right? And then you multiply, okay, 4 times 2 is 8, so 0, 8. 0 longs, 8 units. 2 times 1, that's 2, right? So that becomes 0, 2. So you treat them as just digits, right? 3 times 4 is 12, 1, 2. And 3 times 1 is 3, so 0, 3. And then you count diagonally, sum them up, that's 2. This diagonal will give you combined 12, which gives you 2, and 1 carries over to the next. 1 carries over here. So then this here diagonal gives you, with this 1 carried over, 3. So you put 3, and then that's it, right? And then 0. So the final answer will be 322. Here, 322. 14 times 23. Did we do that here? Don't remember if we did that. yes, 14 times 23. That was the example we did using the above, right? So that was 322 as here using the lattice algorithms. Okay, so let's practice this lattice algorithm. So let's do that, and I'm gonna also do the standard algorithm and expand it just to compare them. Okay, just so we practice and you remember how many algorithms we have. Okay, so 728. Let's put it on top. So 7, 2, 8. And 94, you're gonna put it on the side. Okay. And honestly, just I didn't have to go that far with this. Let me erase that. And I don't need those lines. Okay, so let's do and this every here square field will be split diagonally. Okay, so then let's do 8 times 9, that's 72. 4 times 8, that's 32. 9 times 2, that's 18. 9 times 7, that's 63. Now I'm 4 times 2, that's 8. 4 times 7, that's 28. Right, so again, I multiply every number where they intersected. 8 with 9, 4 with 8, 9 with 2, 4 with 2, 9 with 7, and 4 with 7. And then I start from the right side, the number of units, so I put 2 here, right? Okay. Then I sum up this diagonal. Okay, so that's 13, so that means 3 units and 1 is carried over. Then I sum up this diagonal, that's 24, right? 3 eighths really, so which means 4 and 2 carries over. And then now I have 3, 6, 8, so I put here, and this 6, right? So when I count what's 728 times 94, the answer is 68,432. And you have it. Okay. Okay, now let's do expanded algorithm and then standard. Although that was not a part of this question, but just to practice. So expanded would say, okay, times 4. 4 times 8, right? That's going to give you 32. 4 times 20, that's going to give you 80. 4 times 700, right? That's going to give you 4 times 7 is 28, but remember it's 100, right? Then 9 times 8, that's 72. 9 times 20, sorry, 9, no, my bad. 90 times 8, right? So that's 72 with 10, because that's 9 is really 90, right? Because 94. So 90 times 8, 9 times 8 is 72 times 10, so 720. 90 times 20, so 9 times 2 is 18. But now 90, we're doing 90, so that's, maybe I should write it down. 8, that was 8 times 4, or 4 times 8, the other one 4 times 20. This is 4 times 20. Then we did 9 times 90 times 8. Why am I doing what did I do, guys, here? Oh, then we did, I still forgot about 4 times 700, so I'm going backwards. Now 90 times 8, then we're gonna have 90 times 20, so that's 18 and 2 zeros, right? I wanted you to see it. And 90 times 700, so you can do 9 times 7 and then three zeros, right? 9 times 7 is 63 and 3 zeros. And then you would have to add everything. That's 13, so 1 carried over. That's 24, 4 and 1 carried over. That's 7 and 6, right? Oh, should be 8. 3. That's 2, okay, because that was 24, so that's 8. I made a mistake, and of course it's the same as it was previously. I made a mistake here, was 24, so 2 was carried over, which gave me 8, not 7. Okay, and then standard algorithm, so that was expanded, and the standard algorithm would do the following: 728 multiplied by 94. So we would do, okay, 4 times 8 is 32, 2, 3 carries over. You always record number of units, and the longs are carried to the next spot, right? So then 4 times 2 is 8, plus 3, that's 11. 1 and 1 carries over. 4 times 7 is 28, plus 1, this one here, that's going to be 29. And then 9 times 8 is 72, but we're moving 1 to the left because we're really multiplying by 90. So that's, we can add 0, but we don't have to, right? So 9 times 8 is 72, 2, and we carried 7. And I'm scratching off so I don't confuse what I have now. 9 times 2 is 18, and plus that's 7, that's 25. So 5 and 2 carried over. And 9 times 7 is 63, plus 2, 65. And then you add things, 14, so 4 and 1 carried over, 8, and you have the same answer, 68,432. Okay. Okay,